Ah, damn, there better be another way than this.
Hi, welcome to HoverX. We think there needs to be a better solution as well. Come meet the team and see what we're doing to change human transportation.
Connor Clark, Project and Operations Manager. Robert Farrell, Chief Design Engineer. Matthew James, Chief Propulsion Engineer. Abdul Karim Aksakal, Command and Control Systems Specialist.
The problem HoverX is trying to solve is we believe the automotive industry and human flight has become stagnant. We want to bring innovation back to human transportation.
We were approached by Associate Professor Carl from the University of Queensland to design an innovative flying vehicle that hovered for 2 minutes, 1.5 meters off the ground, and which also showed stable control and maneuverability.
The success of the flying vehicle is extremely important to us for a plethora of reasons. We really believe that personalised human flight in the form of flying vehicle will be a thing in the future, and we're excited to be on the forefront of this endeavour. If successful, the flying vehicle could not only change the engineering community forever, but change human transportation forever as well.
As the Chief Propulsion Engineer for HoverX, my role is to ensure that the flying vehicle achieves liftoff. For engineering design in the modern day, battery-powered vehicles are becoming more and more essential due to the increased demand for a low carbon footprint. For our project, we need batteries that are lightweight, have a high discharge rate and profile, and to be flexible and robust. From thorough research, it was found that lithium polymer batteries will meet our requirements. For our flying vehicle, our goal is to achieve 2 minutes of flight at a hover height of 1.5 meters. To select the optimal motor, a cost versus performance analysis was used. Brushless DC motor manufacturing is typically designed for smaller drones, lifting payloads of a few kilograms, not a human payload. Therefore, the selection of the motor manufacturers for this project is limited to 2, Sunny Sky and Targa Motors. We compared the thrust potential versus cost from both of these manufacturers and highlighted the X6215S motor due to its high performance and competitive cost. This is a 210 kV motor that can produce up to 8.4 kilograms of thrust per motor. To ensure enough voltage is getting to our motors and the flight endurance is reached, 4 pairs of 6-cell lithium polymer batteries will be linked in parallel. This will produce a total voltage of 22.4 volts per battery, producing a thrust of around 100 kilograms. With the batteries at 62% capacity to ensure margin for maneuverability and to protect the motors from overheating. With these motors and batteries in accordance with 16 carbon fibre propellers, the flying vehicle will be able to produce enough lift while being a lightweight and cost-effective solution to human flight.
The challenge that I face is the efficient regulation of 16 individual motors for the pitch, roll, yaw, descent and ascent motions of the flying vehicle to achieve control. Also, given that multicopters are an inherently unstable platform, direct human control of a multicopter and hence our prototype personal flying vehicle is undoubtedly impossible. However, thanks to microelectromechanical systems or MEMS-based flight controllers, the control of our flying vehicle is no longer impossible. Onboard MEMS gyroscopes and accelerometers provide data to the flight controller processor to determine the flying vehicle's attitude and position, which in turn regulates the motor speeds for stability in all phases of flight. The flight controller that we have selected for this project is the DJI NASA MV2, primarily because of its ease of use. Another promising flight controller was the Pixwalk 2.1. However, this flight controller is open source, meaning that the flight code is to be supplied by the end user, which was thought to be a difficult and lengthy task. Furthermore, after realizing that we are going to need more than 8 motors, the Pixwalk 2.1 flight controller was seriously considered, as the DJI only supported up to 8 motors. Through research, we found that by using a Y lead, we could have 2 motors share the same motor channel. That is, our 16 motor configuration is simply an octocopter, as there are only 8 independent motors. As a result, we could use a DJI controller, and based on our design, we could configure the controller as an Octa-V, which is a supported configuration.
When designing the airframe of our personal flying vehicle, we first needed to identify what functions the airframe needed to achieve. We started this process by looking at what designs are currently being tested by other projects. From these, we identified key hazards that our airframe needed to avoid. Since the popularisation of drones in recent years, there's been many attempts by professional and backyard engineers alike to design a personal flying vehicle. The key factor to the airframe's success is the weight of the structure to ensure liftoff. Too much and our motors won't be able to provide enough lift. Too little with smaller, lighter beams, and the structure won't be able to withstand the static load of motors, batteries and other components. To optimise this, we believe that the best design is a cubic space frame. We believe this is great because of its simplicity and how easy it is to optimise to meet the needs of our client. The major hazards that surrounded our design were weight, cost and structural integrity. To handle the static load of our motors, batteries and other components, most current designs being tested out there are outlandish, with cables, support beams and massive structures which are not only hard to model using finite element analysis, but are also too complex to manufacture. The space frame design avoids all this with simple beams that can be easily modelled beforehand and optimised to the correct shape, thickness and length in order to provide enough structural integrity while also minimising weight, which is key for liftoff. Also, the cubic space frame design is successful. It's very easy to see how it can be transitioned into a design that can be marketed for personal use, enclosing the design, improving the aesthetics and making the pilot's controls easily accessible.
In order to complete the project in the limited time frame requested by the client, we divided the major project functions into smaller, more manageable tasks. This was done using a work breakdown structure, which highlighted all the tasks necessary to complete each major component of the project. From this, each task was given a time frame in which to complete it, and all tasks and their time frames were compiled together using a Gantt chart. We gave 7 weeks to research all aspects of the flying vehicle, including locking down where we are getting components from, how much they cost, the mass of each component, performance curves for motors and batteries, estimated flight time, estimated elevation, how all components are mounted to the vehicle, how the vehicle will be controlled, and checking that all electrical components are compatible with each other. From this, we've allotted 4 weeks to receiving funding and procuring parts, and an additional 6 weeks to manufacture and test the flying vehicle.
To summarise, here at HoverX, to achieve our design goals, we are leaning towards using 16 DC brushless motors to achieve liftoff of 1.5 metres. These are powered by a system of lithium polymer batteries to achieve the desired flight endurance of 2 minutes. These are all being controlled by a flight controller that utilises the electric speed controllers to vary motor outputs and perform small controlled movements. The prototype we're presenting today will house all of these components and the pilot in a cubic space frame design. Stay tuned for later in the year when we represent our critical design review of the flying vehicle.